Hello, this is Jeff Hamrick at Rhodes College again, and I'm going to talk with you for a few minutes about how we use a randomization procedure to test the null hypothesis h sub 0 mu equals to mu naught for some particular choice of mu naught. I'll do that with a particular set of data that we've studied in class recently. Recall this set of data with me. It uses information taken from 130 naval recruits. We have three attributes in this set of data: the gender of the recruits, whether or not they were male or female, their body temperatures at some particular moment in time, and their resting heart rates at some particular moment in time. I'd like to collect some summary information about the body temperature data and fathom defaults to produce the sample mean for us, but I want a little bit more than that. I'd like to pay attention to both the sample mean and the sample standard deviation right here and right here respectively. And recall that we see that this mean body temperature is 98.2492 degrees, a little bit less than the so-called wives' tale average or normal body temperature of 98.6 degrees. And so the question arises in our minds perhaps, is it plausible that human body temperature is equal to 98.6 degrees, or do we have enough evidence with this set of data to reject the notion that the true mean body temperature is equal to 98.6 degrees? And so we use a direct simulation procedure to test this idea. Here's how we proceed. Let's create a collection that's going to represent a synthetically produced, a simulated group of 130 naval recruits. So I'll call this collection simulated results. Okay. I need to drag a table off of this box and populate it with 130 cases. Why 130? Because that's the number of naval recruits that were in the original study. And I'm going to call the only attribute I'm going to create here simulated temperatures. Okay? And I'm not going to use an if statement with a random in it like we did to do hypothesis testing for a single proportion. Rather, in this case, I'm going to adopt the philosophy, which we'll justify later, that I'm going to simulate random normal quantities that have a mean equal to what I suspect the mean would be under the null hypothesis, that is 98.6 degrees, and a sample standard deviation equal to that we observed in the original set of data. So I'm going to right-click on this attribute and edit a formula. That formula is going to be random normal. I need to specify a mean and a standard deviation. Remember, under the null hypothesis, okay, that nothing is going on, humans have an average body temperature of 98.6 degrees. That's the wives' tale. I'm going to introduce a standard deviation equal to that sample standard deviation that we observe in the set of data from the study. And here we go. Okay, and if I create the sample mean, if I calculate the sample mean for this particular group, I see that it's 98.5755, quite close to the wives' tale value, the null hypothesized value of 98.6%. So doing this once is not good enough, of course. I'm going to impose a measure on this simulated group of data. It's going to be the mean of the simulated body temperatures. Okay, and the formula is going to be quite simple. It's the mean of the simulated body temperatures, okay? And this is what we saw in our summary box just a minute ago, and I'm going to collect measures here. I'm not going to collect just 5 measures. I'm going to collect something much larger, like 1,000, okay? Well, we can be more bold than that. Let's do 2,000 measures, okay? Done. Let's table off of these measures. Because I didn't replace the first 5, I think I have 2005. Yep, that's fine. I'm going to create a randomization distribution right here. Okay? And I'm going to plot the value of the mean body temperature from the original set of data. That was 98.2492. See, it's right over here. And, oh, that blue line lies completely off of the x-axis scale here, telling us immediately that the empirical p-value is equal to 0. In other words, we have extremely compelling evidence from this set of data that the true mean body temperature is not equal to 98.6%. If you're having trouble computing that empirical p-value or recalling how we do so, just come see one of your professors during their office hours.